The image is familiar. You have seen it thousands of times. In textbooks, on classroom walls, on the covers of science magazines. 8 planets, neatly arranged in a flat ring around a golden star. Each one rendered in crisp color, evenly spaced, obediently circling the sun in clean circular paths. Mercury closest in, then Venus, then Earth, our blue marble, Mars, rusty and cold, then the giants, Jupiter, Saturn with its perfect rings, Uranus tilted sideways, and Neptune, deep blue at the edge of the dark. It is one of the most iconic scientific diagrams in human history. It is also deeply, profoundly misleading. Not because the planets aren't real, they are. Not because the science is wrong. It isn't. But because that diagram, the one burned into your memory, compresses, distorts, and omits so much of the physical reality of our solar system that calling it an accurate representation requires a generosity of definition that science cannot afford. The solar system is not what you were shown. The real one is stranger, more violent, more ancient, and far more difficult to comprehend than any flat illustration on a white background could ever suggest. Start with scale. The diagram you know shows the sun and all 8 planets fitting within a single page. In reality, if you were to draw the sun at a diameter of just 1 inch, roughly the width of a thumb, the Earth would be a grain of fine sand located nearly 9 feet away. Jupiter, the largest planet in our system, would be a small pea sitting about 46 feet from that 1-inch sun. And Neptune, the outermost of the 8 planets, would be that same grain of sand-sized dot sitting roughly a quarter of a mile away. A quarter of a mile, for a diagram that fits on a textbook page. But Neptune is not the edge of the solar system, not even close. Beyond Neptune lies the Kuiper Belt, a wide band of frozen bodies, dwarf planets, and ancient debris stretching from roughly 30 astronomical units from the sun to about 50. 1 astronomical unit is the average distance between Earth and the sun, approximately 93 million miles, or 150 million kilometers. The Kuiper Belt, then, begins where Neptune orbits and extends to nearly 5 billion miles from the sun. Pluto lives here. So does Eris, a dwarf planet more massive than Pluto, discovered in 2005 by astronomer Mike Brown and his team at Caltech. So does Makemake, Haumea, and dozens of other bodies large enough to be classified as dwarf planets, along with hundreds of thousands of smaller frozen objects. And past the Kuiper Belt, there is the scattered disk, a sparse, chaotic region of icy objects flung into wild, elongated orbits by gravitational interactions with Neptune billions of years ago. Some of these objects swing out to distances of hundreds of astronomical units before looping back toward the sun. Their orbits are not the gentle ellipses of the inner planets. They are extreme, tilted at odd angles to the plane of the solar system, some nearly perpendicular to it. Then, farther still, there is the Oort cloud. What is the Oort cloud? It is a theorized, spherical shell of trillions of icy bodies surrounding the entire solar system at distances between 2,000 and 200,000 astronomical units from the sun. At its outer edge, you are almost halfway to the nearest star. The gravitational grip of the sun at that distance is so faint that a passing star or the tidal forces of the Milky Way itself can knock one of these distant bodies loose from its orbit and send it falling inward over thousands of years. These become the long-period comets, those great rare visitors that sweep through the inner solar system once every few thousand years, their tails blazing against the night sky, then vanishing again into the dark for centuries. The solar system, then, is not a flat disk of 8 planets and a star. It is an enormous 3-dimensional structure, extending to distances that make the entire orbit of Neptune look like a small circle drawn on the floor of a football stadium. The planets you know, the ones on that familiar diagram, occupy a thin central wafer of space inside an object so large that light itself, traveling at 300,000 kilometers per second, takes more than a year to reach the Oort cloud's inner edge. Now consider what that diagram does to the orbits. Those clean circular rings drawn around the sun in school books? Real planetary orbits are ellipses, some mildly, some significantly elongated. Earth's orbit is close to circular, but not perfectly so. Our distance from the sun varies between about 91.5 million miles at our closest point in early January, a moment called perihelion, and about 94.5 million miles at our farthest in early July. That 3 million mile difference has a measurable effect on the solar energy our planet receives. Mars has a more pronounced ellipse. Its distance from the Sun swings between roughly 128 million miles and 154 million miles over the course of its year. That variance creates dramatic seasonal differences between Mars's northern and southern hemispheres, far more extreme than anything produced by Earth's more circular path. Mercury's orbit is more elliptical still. At perihelion, Mercury is about 29 million miles from the Sun. At aphelion, it is 43 million miles away. That is nearly a 50% change in distance within a single orbit. Mercury also has the most inclined orbit of any planet in the solar system, tilted about 7 degrees relative to the plane in which Earth orbits, the plane astronomers call the ecliptic. Most of the planets orbit within a few degrees of this plane. Uranus, however, spins on an axial tilt of approximately 98 degrees. It doesn't spin upright like a top. It rolls around the Sun on its side, like a ball being pushed along a floor. The cause of this extreme tilt is believed to be a catastrophic collision with an Earth-sized body early in the solar system's history, a collision violent enough to permanently knock the planet over. The aftermath of that impact is still written into Uranus's geometry today, billions of years later. These are not minor technical footnotes. They are fundamental physical facts about the environment we inhabit, and they are invisible in the standard diagram. The distances between planets in that familiar image are also compressed beyond recognition. The gap between Mars and Jupiter in the diagram looks similar to the gap between Earth and Mars. In reality, the distance from the Sun to Mars is roughly 1.5 astronomical units. The distance from the Sun to Jupiter is 5.2 astronomical units. The gap between them is 3.5 times the Earth-Sun distance, a chasm of roughly 325 million miles. Filling that chasm is the asteroid belt, a region not of densely packed rock as popular culture imagines, but of mostly empty space with scattered rocky and metallic bodies spread so thinly that every spacecraft ever launched through it has passed without incident. If you gathered every object in the asteroid belt and compressed it into a single body, the total mass would be less than 4% of the Moon. The solar system is overwhelmingly empty. That is perhaps the single most disorienting fact about the real structure of our home system. The planets, the moons, the asteroids, the comets, everything visible, everything named, everything studied, represents an almost vanishingly small fraction of the total volume of the space the solar system occupies. The rest is vacuum. Cold, ancient, featureless vacuum threaded through with the Sun's magnetic field and the constant outward rush of charged particles known as the solar wind, which extends in all directions until it finally weakens enough to lose its battle against the interstellar medium, a boundary called the heliopause, located roughly 120 astronomical units from the Sun. Voyager 1, launched in September of 1977, crossed the heliopause in 2012. It had been traveling for 35 years at speeds no human-built object had ever reached, roughly 38,000 miles per hour, and it had just barely left the Sun's direct sphere of influence. It has not reached the Oort cloud. It will not reach the Oort cloud for another 300 years, even at its current speed. The real solar system is not the diagram. It never was. What then are we actually orbiting inside? What is the true structure of this ancient, gravitationally bound system of matter that formed 4.5 billion years ago from a collapsing cloud of gas and dust? And if the familiar image is an illusion of compression and simplification, what does the physical reality of our solar system, its actual geometry, its real dynamics, its chaotic history, reveal about how it came to be and why the planets ended up where they are at all? Because here is something the textbook diagram never shows you. The planets did not form where they orbit today. They moved, dramatically. And that migration changed everything. For most of human history, the planets moved against the will of every model built to contain them. Ancient Greek astronomers watched the night sky with extraordinary patience and noticed something that refused to fit a clean, Earth-centered universe. Mars, Jupiter, and Saturn did not move in simple arcs across the star field. They slowed. They stopped. Then they reversed direction, drifting backward across the constellations for weeks or months before resuming their original course. The Greeks called this retrograde motion, and it was, for nearly 2,000 years, one of the most stubborn puzzles in the history of human thought. Ptolemy of Alexandria, working in the 2nd century of the Common Era, constructed a mathematical system to explain it. In his model, each planet moved along a small circle called an epicycle, and the center of that epicycle itself traveled along a larger circle around the Earth. With enough epicycles stacked within epicycles, Ptolemy could reproduce the observed motions of the planets with reasonable accuracy. His system was not stupid. It was mathematically sophisticated for its era and made predictions that held up well enough for navigation and timekeeping. The Almagest, the treatise in which he laid out this framework, remained the dominant astronomical authority for over 14 centuries. 14 centuries. Then Nicholas Copernicus, a Polish canon working in relative obscurity in the early 16th century, proposed something that dismantled the entire architecture. The retrograde motion of the outer planets was not real. It was an illusion produced by geometry. Earth moves faster in its orbit than Mars or Jupiter. As Earth overtakes an outer planet, that planet appears to slide backward against the background stars, the same way a slower car appears to move backward when you pass it on a highway. Place the sun at the center, set the planets in motion around it at the correct speeds, and the retrograde loops emerge naturally, without a single epicycle required. This was not merely an astronomical correction. It was a complete restructuring of humanity's understanding of its own position in the universe. Copernicus published his heliocentric model in 1543 in a work titled De Revolutionibus Orbium Coelestium. He reportedly received the first printed copy on the day he died. The implications of the book took decades to fully detonate across European intellectual life, but the mechanism he had identified, the geometry of relative motion between orbiting bodies, was correct in its essential structure, even if the perfectly circular orbits he assumed were not. It was Johannes Kepler, working in the early 17th century with the extraordinary observational data of Tycho Brahe, who finally broke the circle. Brahe was the most precise naked-eye observer in history. Working from his observatory on the island of Ven off the coast of Denmark, and later in Prague, he accumulated decades of planetary position measurements accurate to within roughly 1 arc minute, about 1/60th of a degree. No one had ever measured the sky with such discipline. When Brahe died in 1601, Kepler inherited his data. What Kepler found inside that data was not circular orbits, it was ellipses. His first law, published in 1609, states that every planet orbits the Sun along an elliptical path, with the Sun located at one of the 2 focal points of that ellipse, not at the center. This means every planet is sometimes closer to the Sun and sometimes farther from it within a single orbit. The implications for the speed of planetary motion were immediate. Kepler's second law, published in the same year, states that a line drawn from the Sun to a planet sweeps out equal areas in equal times. A planet moves faster when it is close to the Sun, slower when it is far. Mercury, at its closest approach, reaches orbital speeds of approximately 112,000 miles per hour. At its farthest, it slows to roughly 78,000 miles per hour. The difference in speed across a single orbit is dramatic enough to produce one of the strangest phenomena in our solar system. From the surface of Mercury, the Sun would appear to rise, slow down, briefly reverse direction, then resume its motion across the sky. A double sunrise, no fiction, pure orbital mechanics. Kepler's third law, published in 1619, connected orbital period to orbital distance with a precise mathematical relationship. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This single equation, elegant in its simplicity, revealed that the solar system is not arbitrarily arranged. The spacing of the planets, their speeds, their years, all of it is governed by a single underlying mathematical structure. Kepler called it the harmony of the worlds. He was not wrong to see something profound in it, even if the metaphysical framework he wrapped around it was eventually discarded. But Kepler had the laws. He did not have the cause. Why do planets follow these rules? Why do ellipses emerge and not spirals? Why does proximity to the Sun increase orbital speed? These questions waited for Isaac Newton, who in 1687 published Philosophia Naturalis Principia Mathematica and answered all of them with a single force, gravity. Newton showed that every object in the universe with mass attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. From this one relationship, Kepler's three laws fall out as mathematical consequences. The ellipses are not arbitrary. They are the natural geometry of motion under an inverse square force. Every orbit in the solar system, every moon, every asteroid, every comet, every spacecraft traces a path that obeys Newton's law of gravitation with a precision that continues to stagger engineers today. And yet Newton's gravity, accurate enough to land spacecraft on Mars and slingshot probes to the edge of the solar system, is not the final word. Einstein's general theory of relativity, published in 1915, revealed that gravity is not a force transmitted through empty space as Newton imagined. It is the curvature of space-time itself, produced by the presence of mass. In regions of strong gravity, close to the sun, close to massive planets, space-time curves significantly, and the paths of orbiting objects follow that curvature. The difference between Newton and Einstein is small enough to be irrelevant for most solar system dynamics, but not for all of them. Mercury's orbit precesses, the orientation of its ellipse slowly rotates, at a rate that Newton's gravity cannot fully account for. The discrepancy is tiny, 43 arcseconds per century, a shift smaller than the width of a needle seen from 40 feet away. But it is real, measured, and explained exactly by general relativity. Mercury orbits close enough to the sun that the curvature of space-time around our star is just strong enough to leave a fingerprint on the planet's path. The solar system, then, is not just a collection of objects following simple rules. It is a laboratory for the deepest physics we have ever uncovered, a place where Newtonian mechanics, relativistic space-time, orbital resonances, and gravitational chaos all operate simultaneously, on timescales ranging from seconds to billions of years. Which brings the real mystery into focus. The current architecture of the solar system, the precise positions, the orbital spacings, the division between the rocky inner planets and the gas giants of the outer system, did not emerge fully formed from the solar nebula 4.5 billion years ago. The evidence gathered over the last 3 decades of planetary science points to something far more turbulent. The early solar system was a shooting gallery, a dynamical chaos, a place where planets migrated inward and outward across hundreds of millions of miles, where gravitational interactions between the giant planets sent catastrophic waves of debris crashing through the inner system. The orderly diagram in the textbook is the quiet aftermath of an ancient war between worlds. The question that has consumed planetary scientists since the 1990s is precisely this: how did the solar system survive its own formation? How did Earth end up in the narrow habitable zone at just the right distance from the sun, with just the right conditions for liquid water, when the processes that built our solar system were violent enough to reshape entire planetary systems from the inside out? The answer begins not with the planets themselves, but with the giants. Jupiter is the oldest planet in the solar system. That statement alone carries more weight than it first appears. Recent isotopic analysis of iron meteorites, fragments of ancient planetary bodies that formed and were subsequently destroyed in the early solar system, has revealed that Jupiter reached roughly half its current mass within the first 1 million years after the sun ignited. 1 million years sounds like a long time. On a human scale, it is incomprehensible. On a geological scale, it is nothing. The Earth took approximately 100 million years to reach its final mass. Jupiter did half the job in 1% of that time. The reason lies in the physics of planetary formation itself. The solar system was born from a molecular cloud, a vast cold region of gas and dust that began to collapse under its own gravity approximately 4.6 billion years ago. As the cloud collapsed, it spun faster, conservation of angular momentum pulling the material into a rotating disk. At the center, the density and temperature climbed until hydrogen nuclei began fusing. The sun was born. Around it, the remaining material, roughly 1 to 2% of the total mass of the original cloud, formed the protoplanetary disk, a flattened, rotating structure of gas, ice, and fine silicate and metallic dust extending hundreds of astronomical units outward. Within that disk, the process of planetary construction began immediately through a mechanism called accretion. Dust grains collided and stuck together, building pebble-sized aggregates. Pebbles collided and built boulders. Boulders accumulated into bodies kilometers across, planetesimals. The timeline was fast by cosmic standards, measured in thousands to hundreds of thousands of years for the early stages. But accretion has a fundamental speed limit. Beyond a certain size, collisions between planetesimals become destructive rather than constructive. Two large bodies hitting at high relative velocity shatter rather than merge. Something else was needed to build the giants. The leading mechanism, developed and refined over the last 4 decades, is called core accretion. In this model, a solid core of rock and ice builds up first through the normal collision and stick process. Once that core exceeds a critical threshold, estimated at somewhere between 5 and 20 Earth masses, its gravitational field becomes strong enough to capture and hold the surrounding gas of the protoplanetary disk directly. What follows is a period of runaway gas accretion. The planet's mass grows exponentially. Jupiter's core, in this model, reached the critical threshold just as the protoplanetary disk was still gas-rich, early enough to accumulate the 318 Earth masses of material that make up the planet today. Saturn formed by the same mechanism, but more slowly, arriving at the critical core mass just as the gas disk was beginning to thin. It captured less. Its total mass is approximately 95 times Earth's, still a giant, but measurably less massive than Jupiter. Uranus and Neptune, forming even farther out in the disk where material was more sparse and orbital periods longer, took so much time to build their solid cores that by the time they reached runaway accretion thresholds, most of the disk gas was already gone. They ended up as ice giants rather than gas giants, bodies with thick envelopes of hydrogen and helium, but dominated in bulk composition by water, methane, and ammonia in high-pressure forms that behave like neither solid nor liquid as we understand them on Earth's surface. The boundary that separates the rocky inner planets from the gas giants of the outer system is not arbitrary. It is set by temperature. In the early protoplanetary disk, there existed a line, the frost line, also called the snow line, beyond which temperatures were cold enough for water ice to remain stable as a solid. This line sat at roughly 2.5 to 3 astronomical units from the young sun, approximately where the asteroid belt now resides. Beyond it, the surface density of solid material in the disk was dramatically higher, because water, one of the most abundant molecules in the universe, could contribute its mass to solid planetary cores rather than remaining in gaseous form. This abundance of solid material is what allowed the outer solar system to build cores quickly enough to trigger runaway gas accretion. Inside the frost line, where temperatures were too high for ice to survive, only refractory materials, silicates, iron, nickel, remained solid, and the rocky planets formed from a much thinner reservoir of building material. This is why Earth, Venus, Mars, and Mercury are small and rocky. This is why Jupiter and Saturn are enormous and gaseous. The architecture of our solar system is a direct consequence of a temperature gradient set in place by the luminosity of the young sun, written into the disk 4.5 billion years ago. But Jupiter's rapid formation did something else, something that would determine the fate of every other planet in the system. A body as massive as Jupiter does not sit passively in a protoplanetary disk. It interacts with the disk gravitationally in a process called orbital resonance and tidal torque. As Jupiter grew, it carved a gap in the disk, a cleared annular region where its gravitational influence prevented material from accumulating. More critically, Jupiter exchanged angular momentum with the disk material on either side of this gap. Material on the inner edge of the gap was pushed inward, material on the outer edge was pushed outward, and Jupiter itself, in response, began to move. This migration is not a theoretical curiosity. The mathematics of disk-planet interaction, developed rigorously since the 1980s by researchers including William Ward and Doug Lynn, shows that a giant planet embedded in a gas disk will inevitably migrate, the direction and rate depending on the planet's mass and the local disk properties. For Jupiter, the models indicate inward migration. Jupiter formed beyond the frost line and then, under the gravitational torque of the surrounding gas, began drifting toward the Sun. Current estimates suggest Jupiter may have migrated inward to an orbital radius as small as 1.5 astronomical units from the Sun, a position that today sits between Mars and Earth. Had Jupiter continued that inward drift, it would have consumed or ejected the rocky protoplanets of the inner solar system and settled in a position that would have made the Earth as we know it impossible. Jupiter did not continue. Something stopped it. That something was Saturn. Saturn, forming more slowly, eventually grew large enough to become trapped in an orbital resonance with Jupiter, a gravitational lock where their orbital periods settled into a ratio of small whole numbers. The current ratio of Jupiter's orbital period to Saturn's is close to 2:5. Jupiter completes approximately 5 orbits in the time Saturn completes 2. Simulations of the early solar system show that when two giant planets lock into this kind of resonance while embedded in a gas disk, the direction of the inner planet's migration reverses. Jupiter stopped moving inward and began migrating outward, back toward its current position near 5.2 astronomical units, dragging Saturn along with it. This mechanism has a name. Planetary scientists Kevin Walsh, Alessandro Morbidelli, Sean Raymond, David O'Brien, and Avi Mandel described it formally in a 2011 paper published in the journal Nature. They called it the Grand Tack Hypothesis, a reference to the sailing maneuver in which a boat driven in one direction by the wind changes course sharply and heads back the way it came. The consequences of this grand tack were immense. Jupiter's inward migration swept through the primordial asteroid belt, scattering its contents, ejecting the majority of its original mass outward into the outer solar system and beyond. The inner solar system was left dramatically depleted of material. Where perhaps several Earth masses of rocky material once existed inside 2 astronomical units from the Sun, the grand tack left only a thin residue. Mars formed from this depleted reservoir. This is why Mars is so small, roughly 1/10 of Earth's mass. When planetary formation models that ignore Jupiter's migration consistently predict a much more massive Mars. The small size of Mars is one of the most powerful lines of evidence that Jupiter moved. The asteroid belt itself is a graveyard of frustrated planetary formation. Without Jupiter's gravitational interference, the material in that region might have assembled into a planet with a mass somewhere between Earth and Mars. Instead, Jupiter's repeated gravitational perturbations kept orbital velocities in the belt high, too high for constructive collisions. Bodies shattered rather than merged. The total mass of the modern asteroid belt is roughly 4% of the Moon. It is not a planet that exploded, as some older popular accounts suggested. It is a planet that was never allowed to form. What reached the inner solar system during and after the grand tack was not only destruction. The inward scattered material from beyond the frost line, water-rich carbonaceous asteroids and icy bodies from the outer disk, delivered to the young Earth a significant portion of its volatile inventory. The water in Earth's oceans, the carbon in every living cell, the nitrogen in the atmosphere. A measurable fraction of these materials arrived from the outer solar system, transported inward by the gravitational churning that Jupiter's migration set in motion. The same process that nearly sterilized the inner solar system also seeded it. Jupiter is not simply a large planet at a convenient distance. It is the gravitational architect of the entire solar system. Every object inside Neptune's orbit, including Earth, including you, exists in its current form because of where Jupiter went, how fast it moved, and what pulled it back. And Jupiter's role in shaping this solar system was not finished with the grand tack. What came next, hundreds of millions of years after the disk had dissipated and the planets had settled into approximate stability, was more violent still. The gas disk that surrounded the young sun did not last forever. Protoplanetary disks are transient structures. Observations of young stellar systems across the Milky Way, gathered over the last 3 decades by space telescopes including Spitzer and more recently the James Webb Space Telescope, consistently show that gas disks around young stars dissipate within 1 to 10 million years of stellar formation. The primary mechanisms are photoevaporation, in which high-energy ultraviolet and X-ray radiation from the young star strips gas from the disk's surface, and the direct accretion of disk material onto the star itself. Once the gas is gone, the gravitational torques that drove Jupiter's migration cease. The planets stop moving through disk interactions. They settle into the orbits they will occupy for billions of years. Or so it seemed. The early solar system, with its disk gone and its giant planets apparently stabilized, entered a period of relative calm. The four gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, occupied orbits more compact than they do today, all nestled within roughly 15 to 20 astronomical units of the Sun. Beyond them stretched a vast, dense disk of planetesimals, billions of icy and rocky bodies left over from the formation era, extending outward through the region now occupied by the Kuiper Belt. This structure held for hundreds of millions of years. Geologically, the inner solar system was still being shaped. The rocky planets were finishing their formation through large impacts, their surfaces molten and churning. But the outer solar system appeared to be in a holding pattern. Then, approximately 650 million years after the solar system formed, roughly 3.9 billion years ago, something triggered a catastrophe. The evidence for this catastrophe is written in rock, specifically in the rocks of the Moon. When the Apollo missions returned lunar samples to Earth between 1969 and 1972, geochemists began analyzing the ages of impact melt rocks, solidified material fused by the heat of asteroid and comet impacts. The expectation was that these ages would be spread across the Moon's history, with older impacts more common and the frequency gradually declining as the early solar system's debris was swept up. What the data showed instead was a striking clustering. A disproportionate number of lunar impact melt rocks dated to a narrow window between roughly 3.8 and 4.1 billion years ago. The impacts were not randomly distributed through time, they were concentrated. This period acquired a name, the Late Heavy Bombardment, or in more recent literature, the Lunar Cataclysm. The interpretation was stark. Something, approximately 650 million years after the planets formed, had destabilized a large reservoir of rocky and icy bodies in the outer solar system and sent a concentrated wave of impactors crashing through the inner solar system. The Moon, lacking an atmosphere or geological activity to erase the record, preserved the evidence with unusual clarity. The same bombardment struck Earth, Mars, Venus, and Mercury. On Earth, plate tectonics and erosion have erased nearly all direct geological evidence from this era. But on the Moon, the great impact basins, Mare Imbrium, Mare Serenitatis, Mare Crisium, are the scars. What caused it? The answer, developed through a series of computer simulations published in 2005 by a collaboration of 5 planetary scientists working across institutions in France, Brazil, and the United States. Alessandro Morbidelli, Harold Levison, Cleomenes Tsiganis, Rodney Gomes, and their colleagues, is one of the most consequential theoretical results in the history of planetary science. Their work, published as a set of 3 papers in the journal Nature in May of 2005, described a mechanism by which the outer solar system could remain stable for hundreds of millions of years and then abruptly reorganize into a dramatically different configuration in a geologically short time. The model they described became known as the Nice model, named after the city of Nice in southern France where the research was primarily conducted. The mechanism at the core of the Nice model is orbital resonance, the same gravitational phenomenon that eventually halted Jupiter's inward migration, now operating as a trigger rather than a brake. In the initial configuration described by the model, Jupiter and Saturn were closer together than they are today, with their orbital periods close to but not exactly in a 2-to-1 resonance, a configuration where Jupiter would complete 2 full orbits for every one completed by Saturn. As the giant planets slowly drifted outward under the gravitational influence of the outer planetesimal disk, exchanging angular momentum with the billions of small bodies beyond them, Jupiter and Saturn's orbital periods gradually converged toward this 2-to-1 ratio. When they crossed it, the solar system changed in less than 100,000 years. The crossing of the 2-to-1 resonance between Jupiter and Saturn acted as a gravitational amplifier. Their mutual perturbations, previously small and self-canceling, suddenly became large and coherent. Saturn's orbital eccentricity spiked. The gravitational disturbance propagated outward through the giant planet system. Uranus and Neptune, previously in compact orbits interior to the vast outer planetesimal disk, were scattered outward violently, their orbital paths becoming highly elliptical before eventually being damped back to near circular through further interactions. Neptune, in particular, was scattered outward into the dense primordial Kuiper belt, plowing through it like a billiard ball through a rack of tightly packed spheres. The result was the wholesale dispersal of the outer planetesimal disk. Billions of icy bodies were flung onto planet-crossing orbits. A fraction of them, a relatively small fraction, but still representing an enormous absolute number, were directed inward toward the rocky planets of the inner solar system. The Moon's great impact basins record their arrival. The NICE model did not merely explain the late heavy bombardment, it explained simultaneously why Uranus and Neptune are so far from the Sun. They were scattered there. It explained the current orbital inclinations and eccentricities of the outer planets. It explained the structure of the modern Kuiper belt, which is not a smooth, dynamically cold disk, but a complex, dynamically excited population with multiple distinct subpopulations bearing the imprint of Neptune's outward migration. It explained the existence of the Jupiter-Trojan asteroids, 2 clouds of rocky bodies that orbit the Sun at the same distance as Jupiter, 60 degrees ahead and 60 degrees behind it. The NICE model showed these were captured during the resonance crossing event and have been locked in those gravitational sweet spots, called Lagrange points, ever since. No single theoretical model in the history of solar system science had ever explained so many independent observations with a single mechanism. The model has been refined substantially since 2005. A later variant, called the NICE-2 model, adjusted the initial orbital configuration of the giant planets and found that the instability could be triggered by a range of initial conditions, making it more robust. A further development, sometimes called the jumping Jupiter scenario, proposed that Jupiter's movement during the instability was not a smooth drift, but a series of discrete jumps caused by close encounters with a 5th giant planet, a body roughly the mass of Uranus or Neptune that was eventually ejected entirely from the solar system during the chaos. A 5th giant planet, ejected into interstellar space. This is not fringe speculation. The jumping Jupiter scenario was proposed to resolve a specific problem. Smooth migration of Jupiter during the NICE model instability tended to disrupt the orbital structure of the terrestrial planets, particularly the slight eccentricities and inclinations of Earth and Mars, more than the real solar system shows. Discrete gravitational scattering events between Jupiter and a passing ice giant, by contrast, could shift Jupiter's orbit rapidly enough to avoid this disruption. Computer simulations by David Nesvorny and colleagues at the Southwest Research Institute, published in 2011, found that solar system analogs with an initial configuration of 5 giant planets, where the 5th is subsequently ejected, reproduce the current architecture of the solar system significantly more often than simulations starting with only 4. The implication is uncomfortable and remarkable in equal measure. The solar system we inhabit may have formed with 5 giant planets. The 5th, a world the size of Uranus or Neptune, perhaps carrying its own system of moons, was gravitationally ejected during the instability, flung onto a hyperbolic escape trajectory that carried it out of the Sun's gravitational grip entirely. It is, by all probability, somewhere in the interstellar medium now. A rogue planet, cold and dark, drifting between the stars. We will almost certainly never find it. What the NICE model and its descendants revealed, taken together, is that the current solar system is not the solar system that formed. It is the survivor of a violent dynamical reorganization that lasted tens of millions of years, reshaped the outer solar system from the inside out, and sent a wave of destruction into the inner solar system that sterilized, or nearly sterilized, whatever life might have begun to emerge on early Earth during the first 400 million years. Every planet in the current architecture carries in its orbital parameters the memory of what happened during those chaotic hundreds of millions of years. The orbital inclinations, the eccentricities, the locations of resonances between the giant planets, all of it is fossil evidence of an ancient catastrophe, and the catastrophe itself may be the reason we are here. The late heavy bombardment delivered not just destruction but material, water, carbon compounds, amino acid precursors. The same impactors that excavated the lunar basins were crashing into early Earth at a time when its surface had already cooled, when liquid water was already present in some form. The oldest evidence for life on Earth, isotopic signatures in zircon crystals from Western Australia dated to approximately 4.1 billion years ago, places the earliest potential biological activity during or immediately after the bombardment itself. Life, if the evidence holds, did not wait for the solar system to become quiet. It began in the chaos. The architecture that makes Earth habitable, the position of Jupiter as an outer gravitational shield, deflecting long-period comets away from the inner system, the near-circular orbit of Earth stabilized by the Moon's gravitational influence on our axial tilt, the delivery of water and volatiles by early impactors, is not the product of a calm, orderly formation process. It is the product of instability, migration, scattering, and near catastrophe playing out over hundreds of millions of years. The solar system did not arrive at its current state. It survived to it. But the full violence of what the early solar system endured, and the specific moment that came closest to erasing the possibility of Earth entirely, still lies ahead in the record. 4.5 billion years ago, before any planet had reached its final form, the inner solar system was a foundry. The temperatures in the region closest to the young sun exceeded the melting points of iron and silicate rock. Planetesimals, those kilometer-scale building blocks of worlds, collided continuously, merging and shattering and merging again, building progressively larger bodies through a process that was simultaneously creative and catastrophically violent. The energy released by each major impact was not dissipated gently. It was converted directly into heat. The proto-Earth, accumulating mass at a rate that would seem geological by modern standards, but was ferocious by the standards of planet formation, was in its earliest stages largely molten. A magma ocean world, its surface a churning sea of liquid rock radiating infrared energy into the surrounding darkness of the protoplanetary disk. This was not an anomaly. It was the standard condition for rocky planet formation in the inner solar system. Every terrestrial planet went through it. Mars went through it. Venus went through it. The body that would become Earth went through it for tens of millions of years as its mass grew, collision by collision, toward its final value of approximately 6 × 10 to the 24th kilograms, a number so large it resists intuition. If you were to count to that number at 1 count per second without stopping, it would take roughly 190 trillion years. The current age of the universe is approximately 13.8 billion years. You would need to repeat the entire age of the universe roughly 14,000 times to finish counting. That is the mass of the Earth, built grain by grain, rock by rock, collision by collision, over 100 million years of continuous bombardment. And then, approximately 4.5 billion years ago, when the proto-Earth had grown to perhaps 90% of its current mass, something hit it. Not a pebble, not a boulder, not even a small planetesimal. A fully formed protoplanet, roughly the size of Mars, struck the proto-Earth in a collision so energetic that its consequences are still visible every night in the sky above your head. The impacting body is called Theia, named after the Titan goddess of sight in Greek mythology, who was, in myth, the mother of the moon. Theia was not a random fragment of debris. It was a differentiated protoplanet, a body large enough to have developed a distinct iron core and a silicate mantle, the same internal layering that Earth itself had already begun to develop. Its mass is estimated at roughly 10% of Earth's current mass, comparable to Mars. Its impact velocity, relative to the proto-Earth, was probably somewhere between 4 and 10 kilometers per second, between 14,000 and 36,000 kilometers per hour. The collision was not a direct head-on impact in most current models. The leading hypothesis, refined through decades of smoothed particle hydrodynamic simulations, computational models that treat colliding planetary bodies as fluids of billions of particles, each responding to gravity and pressure, describes a grazing, oblique impact. Theia struck the proto-Earth at an angle, like a car clipping another from the side rather than hitting it straight on. The oblique geometry is critical. A direct head-on impact at comparable energies would have buried most of Theia's material deep into the Earth's mantle and generated insufficient angular momentum to account for the Moon's orbit. The oblique strike allowed Theia's outer mantle, the silicate rock layers, to be stripped away and injected into orbit around the proto-Earth, while a large fraction of Theia's iron core merged with Earth's own core. The energy deposited into the Earth-Theia system in those first hours was approximately 100 million times the energy released annually by all of Earth's current volcanic activity combined. The proto-Earth surface was remelted to depths of thousands of kilometers. The impact vaporized a significant fraction of both bodies' outer layers. Within hours to days, a torus of vaporized and molten silicate rock, a disk of magma and silicate vapor, encircled the Earth at distances ranging from inside the Roche limit to several Earth radii beyond it. The Roche limit is the distance from a planet within which tidal forces prevent a self-gravitating body from holding itself together. For Earth, this limit sits at roughly 9,500 kilometers from Earth's center. Material inside this boundary cannot coalesce into a single large body. Tidal forces tear it apart as fast as gravity pulls it together. Material outside it can. Within decades to centuries after the impact, a geological instant, the silicate debris beyond the Roche limit coagulated. Particles collided, clumps formed. The clumps accreted further material. Within a few thousand years at most, the process had produced a single large body, the Moon. The Moon formed so rapidly by geological standards that it was still largely molten when it achieved something close to its final form. The Moon's formation at such proximity to Earth had immediate and profound physical consequences. The Moon, in its earliest state, orbited Earth at a distance as small as 24,000 kilometers, compared to its current mean distance of approximately 384,000 kilometers. At that distance, the gravitational tides the Moon raised on Earth were enormous. Earth's rotation in those early days was much faster. A day lasted roughly 5 to 6 hours. The tidal bulge that the Moon raised on Earth's surface was dragged slightly forward of the Earth-Moon line by Earth's rapid rotation, and this offset bulge pulled gravitationally on the Moon, transferring rotational energy from Earth's spin into the Moon's orbital energy. The Moon moved outward. Earth's rotation slowed. This process of tidal recession continues today, measurably. The Moon recedes from Earth at approximately 3.8 centimeters per year, a rate measured with centimeter-level precision by laser-ranging experiments that bounce laser pulses off retroreflectors left on the lunar surface by Apollo astronauts. Over the 4.5 billion years since the giant impact, this accumulated recession has carried the Moon from its birthplace close to Earth to its current distance, 15 times farther away. The implications of the giant impact extend far beyond the existence of the Moon itself. The collision gave Earth a specific rotational angular momentum and axial tilt, approximately 23.4 degrees relative to the plane of Earth's orbit around the Sun. That tilt is the direct cause of Earth's seasons. It ensures that different hemispheres receive varying angles of solar illumination across the year, driving the annual temperature and precipitation cycles that govern every ecosystem on Earth. Without the giant impact and the specific geometry of the Theia collision, Earth might have been nearly upright with negligible axial tilt and minimal seasons, or tilted dramatically like Uranus, its poles pointing nearly at the Sun for half the year. The Moon, once formed, took on a stabilizing role that amplifies its significance still further. Earth's axial tilt is not fixed on long timescales. Gravitational perturbations from the other planets exert torques on Earth's equatorial bulge, a slight widening at the equator caused by Earth's rotation, tending to shift the axial tilt over time. Without the Moon, numerical simulations by Jacques Lascar and colleagues at the Paris Observatory, published in 1993 in the journal Nature, showed that Earth's axial tilt could vary chaotically between approximately 0 degrees and 85 degrees on timescales of tens of millions of years. An axial tilt of 85 degrees would point Earth's poles almost directly at the Sun, producing extreme polar heating and equatorial freeze in a climate regime nothing like what Earth currently experiences. Mars, which lacks a large moon, has undergone exactly this kind of axial chaos. Its tilt has ranged from near zero to approximately 60 degrees over the past few billion years, contributing to dramatic shifts in its climate history. Earth's moon is large enough relative to its planet, the largest moon-to-planet mass ratio in the solar system among the rocky planets, with the moon representing about 1.2% of Earth's mass, to anchor Earth's axial tilt against these perturbations, holding it within a relatively narrow range of roughly 22 to 24.5 degrees over 100,000-year cycles. This stabilization has maintained climatic conditions on Earth within a range that liquid water and life can tolerate across billions of years. The giant impact hypothesis has not gone unchallenged. Precise isotopic analysis of lunar samples returned by Apollo created a persistent problem for the Standard Model. If the moon formed primarily from Theia's mantle material, as the oblique impact simulation suggested, then the moon's isotopic composition should differ measurably from Earth's, reflecting Theia's presumably distinct chemical history. Theia would have formed in a different part of the protoplanetary disk, at a different time, from material with a slightly different mixture of isotopes. Yet measurements of oxygen, titanium, chromium, silicon, and tungsten isotopes in lunar rocks show the moon and Earth to be nearly identical in composition, far more similar than Earth is to any meteorite type believed to represent other bodies that formed in different parts of the solar system. This near-perfect isotopic match has driven a generation of follow-up simulations exploring alternative impact geometries. One class of solutions, developed by Mattia Chuk and Sarah Stewart and published in Science in 2012, proposes a higher energy impact involving a faster-spinning proto-Earth, in which the collision was more energetic and resulted in thorough mixing of both bodies' mantle material in the post-impact vapor disk, erasing compositional differences through homogenization. Another class of models proposes a series of smaller impactors rather than a single giant one, each contributing material to a growing disk that eventually formed the moon. No single model has fully resolved every constraint simultaneously, and the moon's formation remains one of the most actively debated problems in planetary science. What is not debated is the outcome. The moon exists. Its chemical kinship with Earth's mantle is real. The angular momentum of the Earth-Moon system, the length of Earth's day, the stability of Earth's axial tilt, the existence of the ocean tides that have driven coastal erosion and influenced tidal zone ecosystems across all of Earth's biological history, all of it traces back to a single oblique collision between two protoplanets 4.5 billion years ago, lasting perhaps a few hours from first contact to the dispersal of the impact debris into orbit. The most important event in Earth's history lasted less time than a working day. And in the silence after the impact, as the vapor disk cooled and the moon coalesced and the remelted Earth began the long process of solidifying its second crust, the solar system that had been shaped by Jupiter's migration, by the Nice model instability, by the scattering of the outer planetesimal disk, was settling into something recognizable, not peaceful, not finished, but oriented at last toward the architecture we inhabit today. The question that remains, the one that cuts to the deepest nature of what this solar system is and what it means, is not how it formed, or how it survived its own catastrophes. It is what all of it, taken together, says about the nature of our presence within it. There is a photograph taken on February 14, 1990, by the Voyager 1 spacecraft from a distance of approximately 6 billion kilometers from the Sun. At the request of astronomer Carl Sagan, mission controllers commanded the spacecraft to turn its camera back toward the inner solar system one final time before the camera was shut off permanently to conserve power. In the resulting image, Earth appears as a pale blue dot, a point of light less than 1 pixel across, suspended in a beam of scattered sunlight against the absolute black of space. The entire width of that dot, every ocean, every continent, every mountain range, every person who ever lived, occupies a fraction of a pixel in a single photographic frame. Nothing in the history of human visual culture has more precisely illustrated the physical scale of our situation. But the photograph, as powerful as it is, tells only part of the story. It shows where we are. It says nothing about how improbable it is that we are here at all. The solar system that produced that pale blue dot did not form in an orderly progression from nebula to finished architecture. It was shaped by instabilities, migrations, near catastrophes, and dynamical accidents that could have produced an entirely different outcome at every critical juncture. Jupiter could have continued its inward migration and consumed the inner solar system. Saturn might have formed too slowly to achieve the orbital resonance that pulled Jupiter back. The nice model instability could have occurred earlier, or with greater violence, scattering the terrestrial planets rather than merely bombarding them. Theia might have struck at a slightly different angle, burying its iron core in Earth's mantle rather than merging cleanly with Earth's own core, poisoning the geochemical conditions for life. The moon might not have formed at all, leaving Earth's axial tilt to wander chaotically across billions of years, making long-term climate stability impossible. Each of these outcomes was physically plausible. None of them happened. What this means, precisely, is a question that sits at the intersection of planetary science, statistics, and philosophy, and it has no clean answer. The study of exoplanetary systems, accelerated enormously by the Kepler Space Telescope and its successor TESS, has now cataloged more than 5,000 confirmed exoplanets orbiting stars across the Milky Way. What those catalogs reveal is not reassuring for anyone hoping our solar system is typical. Most planetary systems detected around other stars look nothing like ours. Hot Jupiters, gas giants the size of Jupiter or larger, orbiting their host stars at distances closer than Mercury's orbit, completing a full year in days, are common enough to have been the first exoplanet class discovered, yet they are utterly absent from our own system. Super-Earths, rocky or gaseous planets with masses between 1 and 10 times Earth's mass, are the most abundant planet type in the galaxy. Our solar system contains none. The gap between Earth and Neptune in our system, filled only by the sparse asteroid belt and the failed formation of Mars, is occupied in most other systems by one or more massive planets. Our solar system's architecture, its complete absence of hot Jupiters and super-Earths, its large gap between the rocky inner planets and the ice giants, its relatively circular planetary orbits, its stable habitable zone, appears to be the minority outcome, not the default. The grand tack, the nice model instability, the giant impact that formed the moon. These events did not just shape our solar system. They may have produced the specific set of conditions that allowed a stable, water-bearing, axially anchored rocky planet to persist in the habitable zone of a middle-aged star for 4.5 billion years, long enough for life to arise, persist through mass extinctions, and eventually develop the cognitive capacity to look back and reconstruct the history of the system that produced it. The Sun itself is a participant in this story, not merely a backdrop. It is a G-type main-sequence star, a yellow dwarf, currently about halfway through its approximately 10 billion-year hydrogen-burning lifespan. At 4.6 billion years old, it fuses roughly 620 million metric tons of hydrogen into helium every second in its core, releasing energy that has warmed Earth's surface continuously since the Hadean Eon. The Sun's luminosity has not been constant across that time. In its youth, the Sun was approximately 70% as luminous as it is today, a fact that creates the so-called faint young sun paradox. Earth's early geological record shows evidence of liquid water and mild temperatures during a period when solar models predict the Sun was too dim to maintain above freezing temperatures at Earth's distance. The resolution likely involves higher concentrations of greenhouse gases, carbon dioxide, methane, in the early atmosphere, together with the lower albedo of a young Earth with less continental landmass and a different cloud cover regime. The paradox is not fully resolved, but its existence underlines something important. Earth's habitability has never been a fixed property. It has been a dynamic balance, continuously maintained against a changing sun, a shifting atmosphere, and the slow geological cycling of carbon between rocks, oceans, and air. In approximately 5 billion years, the Sun will exhaust its core hydrogen supply. The energy-generating shell will expand outward, and the Sun will swell into a red giant, its outer layers expanding to roughly 200 times the current solar radius, reaching or surpassing Earth's current orbital distance. Whether Earth is engulfed depends on the precise details of solar mass loss during the red giant phase and the outward migration of Earth's orbit as the Sun sheds mass. Current models suggest Earth may just escape engulfment, but will be stripped of its atmosphere and oceans long before the sun reaches maximum red giant size. As solar luminosity increases dramatically in the final billion years of the main sequence phase, the oceans will boil, the atmosphere will be lost to space. The surface temperature will climb to values incompatible with any known biochemistry. This will happen gradually over hundreds of millions of years, not a sudden event, but a long, irreversible transition from a living world to a scorched remnant. This is not a tragedy in any cosmically meaningful sense. It is the standard life cycle of a rocky planet orbiting a star of the sun's mass. Every star of this type eventually becomes a red giant. Every inner rocky planet eventually faces the same fate. The universe does not issue exceptions. What is extraordinary is the window. 4.5 billion years of stable solar output, stable planetary orbits, stable axial tilt, stable liquid water. That window, already 3/4 closed from Earth's formation to the present moment, is precisely what allowed the entire history of life on this planet to unfold. The Cambrian explosion of complex animal body plans. The colonization of land. The diversification of flowering plants and the insects that co-evolved with them. The emergence of hominids in Africa 3 to 4 million years ago, and the specific lineage of Homo sapiens approximately 300,000 years ago, with the cognitive architecture to ask questions about stars and build instruments sensitive enough to answer them. All of it, the full span of Earth's biological history, fits within the stable window that the solar system's improbable architecture created and maintained. The planetary scientists who reconstructed this history did not do so with telescopes pointed at distant stars. They did it with lunar rocks, meteorite isotopes, computer simulations, and the centuries-long accumulation of orbital mechanics stretching back to Kepler's pencil and compass work on Tycho Brahe's data. They found, written in the chemistry of ancient minerals and the mathematics of gravitational resonance, a coherent narrative of formation, catastrophe, migration, and stabilization. The solar system is not a collection of objects following simple rules. It is a record, a 4.5 billion year record of every force that acted on it, preserved in orbital parameters, isotopic ratios, crater densities, and the chemical composition of the air and water and rock of every world in it. Earth is part of that record. So is the moon. So is the asteroid belt, the precise spacing of the giant planets, the inclination of Uranus, the trajectory of Voyager 1 still moving outward through interstellar space at 38,000 miles per hour, its golden record carrying the sounds of Earth into a darkness it will traverse for billions of years before encountering anything at all. The diagram on the classroom wall was not wrong to try to capture this. It was simply too small a frame for what it was attempting to show. The real solar system cannot be drawn on a page. It can only be understood through the physics that governs it, the same physics that traces the ellipse of every orbit, curves space-time around every mass, and connects the collapse of a molecular cloud 4.5 billion years ago to the specific configuration of atoms currently forming the thoughts in your mind. You are not separate from this system. You are made of it. The iron in your blood was forged in stellar interiors that exploded before the sun existed. The calcium in your bones, the oxygen you breathe, the carbon in every molecule of every cell in your body. All of it was synthesized in nuclear reactions inside stars, dispersed by stellar winds and supernovae, incorporated into the molecular cloud that collapsed to form the sun, processed through the violence of planetary formation, delivered to Earth's surface by impacts and volcanic outgassing, cycled through oceans and atmosphere and living tissue across billions of years, and assembled, by evolution, into the particular arrangement of matter that is reading these words right now. The solar system you know is an illusion. The one that actually exists, ancient, violent, improbable, and staggeringly precise, produced you. That is not a small thing.